first thing we're going to do is discuss functions and some other preliminary results. Now, we're not going to go in too much depth as we cover these preliminaries, but as the semester goes, we will see that many of these results show up, and as we keep using them, they will become more natural. So first, we'll talk about functions. We'll be dealing with many different kinds of functions this semester. So we'll start with a definition. A function consists of a set of inputs, a set of outputs, and a rule assigning exactly one output to each input. This last part is important. We'll see a graphical interpretation of that last part in a moment. But before that, let's set a little more of the language. And I have these as remarks. So first, we call the set of inputs the domain of the function, of a function. And we call the set of outputs the range of a function. And for our purposes, we'll largely be considering functions on the Cartesian plane with x's and y's, well, x's and y's. And we'll let x denote each input, or we'll let x denote a set of inputs, and we'll let y denote the output associated to an input. So let's look at some examples. And we're going to look at some graphs of, we'll look at some graphs, and here we'll detect whether these graphs represent functions. So first, on our graph, remember the horizontal axis will be our x values, our inputs. The vertical y-axis will be our outputs. And let's say this line, well, this squiggly line represents a set of inputs and outputs. And the question will be, is this a function? We'll have a couple examples. The question for all of these will be, is this a function? Does this line represent a function? Well, set of inputs, set of outputs, yeah, okay, we have them. There is a set of x values associated with that. There's a set of y values associated with that. But the third part, does that relation assign exactly one output to each input? Well, let's look at a couple specific inputs. What if we take this input, whatever that x value is right here? Is there exactly one output for this input? Well, if you go up here, there's only one x-y pair associated with that x value. So that's okay. What about this x value over here? Maybe I'll mark them off like that. As you can see, we can't do every x value. There is a large infinite number of potential x values, but we can look at some of them and generalize. So we looked at this x value. What if we look at this x value? How many outputs? The rule for functions says exactly one output to each input. Well, here's an input. Up here, there is exactly one y value associated to that. Well, what if we go over here on the left side of the y-axis? Well, this is a given input, and again, there is only one output. And you can do that for any of these x values. So we'll say, yes, this is a function. Because we have inputs, we have outputs, and each input has exactly one output. What about this example? Does this give a function? There's a good chance this actually is going to be the last time I label the horizontal axis with an x and the vertical with a y. That is standard. So usually I'll just write it like this with the assumption that the horizontal is the x and the vertical is the y. What if we take the set of x and y pairs given by that curve? Well, let's do the same thing. Let's look at the rule and let's see if it assigns exactly one output to each input. Well, let's start here. Well, if we take that input, how many outputs are there? Well, there's just that one y value. So that's okay. What about, I don't know, here? That's a good next one to do. What about here? Well, right there, there's only one y value, one output corresponding to that input. Well, what if we choose this right here? Well, how many y values correspond to that x value? Well, we go down here, there's one. We go over here, there's a second one. Up here, there's a third one. So for this x value, there are multiple outputs. All you need is one x value that violates that last value, that last condition for a function. So no, this is not a function, given that notation. And this example, we can actually see, well, we can use this example to get a visual for what might happen that prevents a given graph from being a function. Well, a given input is just an x value. And if there are multiple outputs for a given input, the vertical line that hits that x value is going to hit the graph more than once. Over here, if you take a vertical line, it's going to hit it only once. Such a phenomenon would correspond to a rule assigning exactly one output to each input. But here, we have this vertical line hitting this graph multiple times. That corresponds to a given input, a given x value, having multiple corresponding y values. So let's record that as a theorem. This is a theorem for detecting whether a graph is a function, a given graph is a function. And we'll call it, we use a vertical line, we'll call it vertical line test. So vertical line test. It's a theorem. A theorem in math means a relatively large and important result. Theorem, T-H-E-O-R-E-M. And this is an example of a theorem. The graph of y, so the graph of y meaning the graph defined by this set notation. The graph of y defines a function if and only if each vertical line intersects the graph. Well, if it intersects the graph more than once, it's not a function. So if any vertical line intersects it exactly once, that is a function. But in particular, we'll look at the next example. There will be vertical lines where it doesn't hit the graph at all. And that's not a problem. But the problem occurs when a vertical line intersects the graph more than once. So the graph will define a function if and only if each vertical line intersects the graph no more than once. Now in that statement there's the phrase if and only if. In math, if and only if actually says two things. I'm not going to ask about how to logically interpret if and only if. If and only if in math is used to describe two different things which are logically equivalent. So what happens before the if and only if is logically equivalent to what happens after if and only if. So the graph defines a function is exactly the same as each vertical line intersects the graph no more than once. And on this one that I drew here, and I erased half of, you can rewind a few seconds to see the whole thing again. each vertical line intersects it exactly once. In particular, each vertical line intersects it no more than once. So that was a function. Over here, in this second example, a vertical line here intersects it exactly once. Well, that's okay. That doesn't really tell us much. We need each vertical line to intersect no more than once. And you can see there are vertical lines in this middle piece of the graph that intersect the graph more than once, 2 or 3 times. So that is not a function, which you can conclude by the vertical line test. Let's look at one more example. Let's take that circle. And the question here would be, does this graph define a function? We have a circle. Well, let's use the vertical line test. How about a vertical line here? Vertical line here intersects it 0 times. That's okay. 0 is no more than 1. How about a vertical line, say, here? It's a lousy vertical line. That's supposed to be right on the edge of that circle. Well, I mean, if circles have edges, which they don't. This vertical line I drew in the hopes that it would look like it's hitting the circle, the curve, exactly once. Let's say that. So that vertical line doesn't prevent this from being a function, but of course, if you take a vertical line, well, take the y-axis. The y-axis is a vertical line. It hits the curve twice, and if that happens more than 0 times a vertical line hitting it twice, then it is not a function. So this is not a function by the vertical line test. Now, one of the things we're going to do quite frequently throughout the semester is to consider graphs of functions, and later in the semester we'll see how we can use calculus to actually sketch a graph of a function. But for now, we don't know calculus yet. For now, let's look at several important functions. The graphs of several important functions. And knowing these graphs will help us many times throughout the semester. So let's call this important functions to know. Important functions to know. Graphs of important functions to know. I'm going to use a different marker, one that's less dead. This one should work. Important functions. Well, here's a graph of an important function. We have our x and y axis. Right here we have the parabola. This is given by y equals x squared. When the graph defines a function, we'll actually use a functional notation, which I'll introduce here. If the graph gives a function, we'll use this notation, f parentheses x end parentheses, read f of x. Right here we have f of x equals x squared. Goes through the point 0, 0. We will use ordered pairs for points when we actually label them. We haven't done that yet. So there's one function. Let's do this function. There are going to be 6 functions in this, under this important functions to know. X cubed, something like this. Going up like that into quadrant 1, going down like that into quadrant 3. Square root of x. Which looks like that. Notice the domain, the potential inputs for these first 2 are all x values, infinity, negative infinity to infinity. The domain over here is not all x values, it's just 0 to infinity, including 0, because we can't take a square root of a negative number. Let's look at 3 more, which we'll see. Right here, Here's f of x equals 1 over x. Notice you can't put x equals 0 into this because you get 1 over 0. And that's shown in this because nothing occurs when x equals 0. Goes up like that, over like that in quadrant 1, and similarly in quadrant 3. Now these, we're going to just sketch these and use sketches of these. So the drawings don't have to be perfectly to scale. They just have to be enough to scale. In what we're about to do with these, I'll label a little bit. 1 over x squared. So notice here all of these corresponding y values are above the x-axis because we squared. This, we could get negatives because 1 over a negative is a negative. And last function for now is absolute value, which is actually a piecewise function, and we'll see what we mean by that in a moment. So we have these 6 functions. The graphs of these functions are important to know. What we're going to do with these is use these graphs to create, well, use these graphs and a couple properties to create more graphs. So let's do a couple sketches of graphs using these graphs. Example. Sketch using graph transformations is what we're going to use. I'm not going to write that, but sketch using graph transformations a graph of f of x. Let's use the absolute value as our main function. 2 absolute value x minus 4. So we have 2 times absolute value of x minus 4. And what we're going to do with these, well, the first observation is to figure out which of these 6 this is going to start as. Well, which of these 6 are we going to transform into this function? And this has an absolute value of x as its, base function, you could say. So it's going to start by looking like this, and then we're going to transform it using those numbers. So let's do that. I might erase this in a moment. Yeah, I probably will. So we're going to start right here. What we're going to do is start with the absolute value function and then build 2 absolute value x minus 4. And the way we do that, well, we start with our absolute value function. On these, well, with these, I like keeping track of one important thing on the function. For the first 3 and that last one, the important point will be the point 0, 0 at the beginning. For these, it'll be what happens at 0. We'll see that in the next example, or maybe the third example. So what is the first thing that happens to this x? Well, the first thing that happens to this x is this negative 4. So what we're going to do is sketch x with a negative 4 inside the absolute value. Well, how is that reflected? Well, you could memorize a bunch of rules. I find the rules a little, well, I find them easier to do by considering a point than I do by considering a list of rules. So what happens here at this point? Well, at 0, 0, what's inside the absolute value is 0. Where is the inside of this absolute value? 0. Where will what happens inside the absolute value be 0? Well, if x equals 4, then you have absolute value of 4 minus 4, which is 0. So this point 0, 0 is going to move over to 4. Giving us the point 4, 0. That looks lousy. I have an eraser, so if I draw something lousily, I can just erase it. Which is fortunate for me. Doesn't really do much for you. There, that looks better. And that arrow doesn't look all that, but that looks okay. So notice what happens here. The rule that you could memorize is that if there is a negative attached to the x like that, well, and if it's x with a negative number being added to it, the entire graph shifts to the right 4 units. If it's positive, it shifts to the left. I like just keeping track of this point. Well, what else happens? Well, we have a 2 on there. What does that 2 do? Once we take care of this 2, we'll be done with this one. We want to deal with this 2 next. Well, if we look at that point 4, 0, 2 times 0 is still 0, so that doesn't do anything. But what if you take a point like this? Whatever this x value is and that corresponding y value. Well, on this graph, it is here. But what does that 2 do to that point? Instead of giving this y value, it's going to give 2 times that y value, which is 2 times higher. And that'll happen for all of these points away from 0. All of these points are going to go 2 times as high. And when that happens on all of the points, it causes the graph, it's still going to start at that point 4, 0, because 2 times 0 is 0. But all of these points go higher. Starting at this point, what that looks like is the graph getting narrower. So right here, this is a more, pinched in V, I guess you could say. And we have our function. Let's do one more thing to this. Let's say instead of asking for 2 absolute value x minus 4, I ask for, 2 absolute value x minus 4. Let's throw a plus 3 on there. What does that plus 3 do? Well, I don't have another board to write this on, so I would normally draw this right after that, but I don't want to squeeze it there, so I'm just going to put it on this board. Guess I could have put it there. Yeah, I'm going to put it there. This is the original. 0, 0. I should label that since I labeled it before. So I'm going to draw this one here. Well, what happens if we take that graph and add a 3 to it? Well, this plus 3, what happens to each point? Well, instead of being at 4, 0, that's going to be at 4 plus, or that's going to be at 4, 0 plus 3. So it's going to lift up 3 units, meaning that this point, instead of being here, is going to be 3 units higher. So instead of 4, 0, that point's going to be at 4, 3. And adding 3 to this function is going to cause all of these points to go up 3 units. So this plus 3 is going to cause that entire graph to lift by 3 units. And we can see that by just taking this point 4, 0, seeing what happens to 4, 0, it goes to 4, 3, and dragging the rest of the graph along with it. So that is the label for that function. Let's look at another. So in that one, we started with absolute value. We looked at what happened to x. It moved over 4. Then it became narrower. And then it lifted up. If this 2 were like a half or something, it would expand out a little. But that 2 was a 2. So it became narrower. And then the 3 lifted it 3 units. So I guess we technically did 2 examples there, since I threw that plus 3 on it. Let's do another. Let's do sketch a graph of 1 over x plus 2. 1 over x plus 2. So which of those 6 does this look most like in its most basic sense? So when I'm looking at things in calculus, to understand the behavior, you can actually ignore a lot of what's going on with the actual numbers. So right here, this plus 2 is really just in the way, and it's preventing us from just seeing this as 1 over x. So if we want to sketch a graph, let's start with 1 over x. Put the label over here. 1 over x, which looks like this. And what happens to that 1 over x? Well, we take a 2 and we put it on the x, and we get, what, f of x equals 1 over x plus 2. How can we see this transformation? Well, we can use that remark I had before when going through the first example. This plus 2 will cause it to shift to the left 2 units. But why does that happen? Well, I like to look at what happens at 0, at x equals 0. In this case, nothing in the graph happens at 0. But notice, this graph is in a way symmetric about what happens at 0. So if we detect what happens there, we can just drag the graph along with it. Now when x equals 0, this denominator is 0. So what we're really looking for is where the denominator is 0. When is this denominator 0? Well, that denominator is 0 when x equals negative 2. And I'm going to label that with a dotted line for now. So what happens here at 0 is now going to occur at negative 2. And then we just have to drag the rest of the graph along with it. And I guess I'll just fit it in on this. Let's draw it like that. Now, what else can we do with this one? There's one other transformation we haven't really considered. So let's do that here. Let's add another thing to this. Let's throw a negative sign on. What does that negative sign do? Well, it takes this function and makes all of the y values negative. So it takes this, makes all y values negative. What does that mean, make all y values negative? Well, instead of this point going up here at, say, I don't know, positive 5, at y equals positive 5, that's going to go down here and happen at negative 5. And that'll happen for all of these points. All of these y values are going to become their negatives. Well, what does that mean? This goes down here, and this down here will go up here. So that negative will cause this entire graph to flip over the x-axis. This negative 2, you flip that dotted line over the x-axis, it's just going to stay the same. But if you flip the rest over the x-axis, on paper you can just fold the page over the x-axis and then see where the graph goes. This is going to go now under the x-axis, and this piece is going to flip over the x-axis, and it'll look something like that. So this is what? F of x is negative 1 over x plus 2. One other thing we can do is describe a graph in pieces. And we call that a piecewise graph. So let's just do one quick example of a piecewise function. We'll see these a few times throughout the semester. We'll introduce some more notation for it and then do an example. So we'll say, for this example, sketch a graph of the piecewise function, P-I-E-C-E, piecewise function, W-I-S-E. And we're going to define this function in pieces. We'll define this one in 2 pieces. And we'll use a curly brace for it. So let's say it's x cubed. When is it x cubed? For x values less than or equal to 0. And let's say, no, that one won't look that good. Let's just say 1 over x squared for x larger than 0. So we have two different pieces of the function to consider. What happens before 0 and at 0, and what happens after 0. So let's draw this. So first, we want x cubed before and equal to 0. Well, what does the graph of x cubed look like? Well, that was one of those 6 graphs. It looks like this. Which piece of this occurs before or equal to 0? Well, that's equal to 0. Before 0 is that hunk of the graph. So let's draw that. And at 0, we have that point. We'll draw that point because we want it to be clear that that is there. And then after 0, this function is 1 over x squared. What does 1 over x squared look like? I'll just put that here. 1 over x squared. Remember, looks like that. And we want the piece after 0, so that'll be this piece. So this will look like that, and I'll just call this f of x. You could say f of x equals all that stuff, but I'll just say f of x since that's this example. So it's defined in two pieces. The one piece is this part before or equal to 0, and the other piece is that piece after 0. Now, the next thing we're going to do is look at more specific functions and look at some properties of some specific functions. In particular, we are going to look at lines and polynomials, some polynomials. So let's do